Okay, so next I just want to talk briefly about the action potential of a cardiac muscle cell and just briefly kind of compare that to a excuse me, to the action potential of a neuron and talk a little bit about the differences between them. All right. Now, basically, when we take a look at this graph here, what we're seeing here is time on the bottom in milliseconds, and then we're seeing the membrane potential in millivolts. All right. Now, what you'll note now in yellow, I have the action potential of a neuron, and then in green, I have the action potential of a cardiac muscle cell. And as you can see, they are significantly different. All right. Now, the events are very, very similar. There's just really one major difference between the two, and that's this plateau phase that you see here. Okay, so let's kind of talk about this. I mean, you already know how the neuron, the events of a depolarization of a neuron. You have this upward spike is an influx of sodium, and then this rapid downward spike is an efflux of potassium, and then the sodium. Then we'll hyperpolarize, and then the sodium potassium pump will reset us back to our membrane potential. And this happens. The action potential of a neuron, remember, happens 3 to 5 milliseconds tops, depending on what type of neuron we're talking about, how big it is, how myelinated it is. Okay, but regardless, it's still a very fast occurring event. All right. Now with a cardiac muscle cell, when those autorhythmic or those pacemaker cells, when they depolarize the cardiac muscle, there's a lot more time involved in involved in exciting the cardiac muscle. Now remember, the whole point of this action potential of a cardiac muscle is to basically get it ready to contract. Okay, so the action potential excites the muscle cell, and then that stimulates the release of calcium, gets the actin and myosin going, the actual contraction events, to make the muscle shorten, which makes the muscle pump. That's the whole point of this excitation part, is to stimulate the muscle to contract. All right. Now, as you can see, I have different phases numbered on this graph. Okay. Now let's kind of take it. Now let's talk just a little bit about this, about these different phases or these different swings you see on the graph. Now, when you look at phase 0, that's exactly the same as the action potential of a neuron. It's a very similar upward spike, and all it is just an influx of sodium. Once the cell gets excited a little bit, sodium gates open, and then bang, you see a very rapid change in membrane potential. Now remember that the resting membrane potential of a cardiac muscle cell is around negative 90 millivolts. Okay. So, and then what happens is you see the upward spike, and then just like with a neuron, you start to see the spike go down. And what's happening there in phase 1, that's the initial repolarization. Because just like with a neuron, once the charge of that cell gets very positive, those electrically sensitive gates, those potassium gates open, and then potassium goes rushing out. But there's a little differences, subtle differences you can see here. And that's phase number 2, the plateau phase. Okay, now the plateau phase, what this is a very slow influx of calcium. Okay, so once we reach a resting membrane potential of, once we start getting around negative 40 millivolts and start getting around 20 to 25, positive 25, that's going to stimulate calcium gates to open. Okay. And that's going to slow down the rate of the depolarization because now we're pumping in even more positively charged ions. Okay, so calcium is going to start to diffuse into the muscle cell, and that's what causes this plateau phase. That's what prevents this action potential, this cell, from just repolarizing at a very rapid rate. So we plateau at a fairly positively charged state, and the whole purpose behind this is cardiac muscle is a little different than skeletal muscle in the regard that the influx of calcium stimulates the sarcoplasmic reticulum of the cardiac muscle to release the stored calcium within the muscle itself. I know it's a little odd, but that's just how it works. Whereas with a skeletal muscle, that wave of depolarization, that change in the electrical charge along the sarcolemma, along the membrane of the skeletal muscle, that's enough to stimulate the SR to release its stored calcium. Okay, so then calcium is going to start to diffuse inward, and then eventually And then eventually what'll happen is, you know, what'll happen is phase 3 is the repolarization phase. There will be pumps that'll start to pump the calcium out. There's already pumps moving the sodium out, and then we will repolarize as potassium is moving out as well. So all these positively charged ions are getting shuttled out of the cell, and then that's causing this big downward spike. And then phase number 4, all that is that's just when we reach our resting membrane potential. That's what I have abbreviated RMP, resting membrane potential. Okay. Now, this is kind of an important thing to discuss about this as well is the force of the contraction. Okay, and that revolves around how much calcium is available to diffuse into the cell. Excuse me. Now, basically, if we kind of graph this out, let's say this blue line right here is the force of the contraction. Okay, what you'll notice is that the cardiac muscle cell reaches its peak force, meaning it's the strongest part of the squeezing, the pumping, the contracting action, when we reach the highest amount of calcium entering the cell. Okay, so what we're saying here is the more calcium that diffuses into the cardiac muscle cell, the more force that it's going to contract with. Okay, the more force that's going to make the muscle cell contract with more force, and that's going to generate a stronger pumping action, and that's also going to help increase blood pressure. Now, in the situation like exercise, that's a necessary thing. You need to pump more blood with more force, and blood pressure needs to be higher so you can perfuse your muscles and active tissues with blood. Okay, and by understanding these electrochemical events, that's where they kind of came up with these medications called calcium channel blockers. They're used to treat people that have high blood pressure, hypertension. So if we block or limit the amount of calcium that's available to get inside of the cell during this action potential, that can ultimately help lower blood pressure, because if the cardiac muscle is contracting with less force, that's going to lower blood pressure in the vascular system. Okay, and that's all that goes on here during the action potential of a cardiac muscle cell once we depolarize the cell. Okay, again, that the inward movement of sodium from a pacemaker cell or an adjacent muscle cell, okay, through the gap junctions, that will stimulate sodium specific gates to open, and that will cause a rapid depolarization. And then we'll start to repolarize, but like we said earlier, calcium gates are going to open, and that's going to slow this down. And then eventually the heart's going to the muscle cell is going to repolarize. I mean, at the heart of the cardiac muscle cell. And then that's just an efflux or an outward movement of potassium, and it'll eventually reach its resting membrane potential. Okay. Oh, and the total timeline for this is 300 milliseconds. Okay, it takes about 300 milliseconds to depolarize the cardiac muscle cell. Now, again, that's advantageous also because this just gives the heart, these chambers, just a little more time to fill with blood. Okay, it gives the chambers a little more time to fill with blood, and this also aids and plays a role into the actual pumping action of the heart, which makes it just so much more efficient at its job. And we'll talk about that more in detail when we talk about the cardiac cycle. So this is the cardiac muscle action potential.